Hey, welcome back. This is 10.3, continuing on with chapter 10. We want to connect now this stuff with parametric equations to calculus. So most of the stuff we've been doing so far is just kind of considered almost pre-calculus material, and you probably did see it in pre-calculus. But now we want to introduce the ideas of first here, the derivative, and then secondly, we'll look at the integral, I believe, in 10.5. Okay, so anyways here, 10.3, basically the derivative, one of the first things we need to get out of the way is the definition of a smooth curve. And basically this is just where the derivative can fail. So basically the definition from the book, a curve, C represented by a set of parametric equations, x equals f of t, and then y equals, let's say, g of t on some interval I, is called smooth if it doesn't have any sort of kinks in it. And the kinks will be caused by having like a simultaneous equaling of 0 from the derivatives of these component functions for x and y. So the curve C represented by x and y on some interval I is called smooth if our f prime and g prime are continuous and not simultaneously 0. Except possibly at the endpoints of the interval. Sorry about my writing. Okay. So in particular, we were working with the cycloid in the last section, so recall the cycloid. And this gives a pretty good idea of the issue. Okay. So our cycloid was kind of like a bunch of humps created by the rolling of a circle. It just keeps on going like that. And our functions, x was, we use a parameter theta, but let's just for the sake of consistency use t, like with the definition. X equals a times t minus sine t, y was equal to a minus a cosine t. Okay. We wanted to know where the cycloid is smooth, basically. So to figure this out, what you do is kind of just take the derivatives of the parts. Okay. So take the derivative of x with respect to t. And of course, if you distributed and took the derivative, you get a minus a cosine t. And then you get the derivative of y with respect to t. And here the derivative of a is 0, the derivative of cosine is negative sine, so you get negative a sine t, so positive a sine t at the end of the day. Okay, so this thing won't be, first off, both of these functions are continuous everywhere. Okay, the only issue for smoothness might be if the derivatives, okay, are simultaneously equal to 0. So we take the derivatives and set them equal to 0 and solve. So we have a trigonometric equation, basically. We can say a cosine t is equal to a, and we assume a is not 0. Okay. So I could divide both sides by a, and I get cosine of t is equal to 1. Okay. So then in this case, the solutions, again, you think about the unit circle when you're kind of getting the solutions. Cosine is positive 1 when t is equal to 0, and then plus any 2 pi rotation. That would get you back to 0. Okay? So basically, it'll happen at even multiples of pi. So always right here on the unit circle. Okay, let's look at the other guy. So a sine t, set that equal to 0. So you're asking yourself, where is this thing going to be equal to 0? You could divide out by a if you want, and then just ask yourself, where is sine equal to 0? And sine will be equal to 0 at not just 0, but also then at pi. So t would be 0 plus any 2 pi n, or 2n pi. And then the other set of solutions would be pi plus 2n pi. But of course, we could combine these together to just write it as one set, t equals 0 plus n pi. In other words, t is equal to n pi. Okay. Right, so the places where it's simultaneously going to be equal to 0 will be at these where it's equal to 0, or any add in 2n pi to that. So it's basically just going to be from right here. Okay. So at the end of the day, the curve is not smooth. When your t values are even multiples of pi. And then we can also note then the xy coordinates of those points. So x would be a times 2 pi n minus sine of 2 pi n. And that would be 2 pi a n minus, well, sine is always 0 at those even multiples of pi and the odd multiples of pi. So that extra part would just be 0. So x would equal even multiples of pi a. And then the y value, excuse me, a minus a cosine of 2 pi n. And cosine is 1 at those places, so it's going to be a minus a, which will equal 0. And if you go back and look at our work with the cycloid in the previous section, let's see if I can find where that was. So it would have been 10.2. Where's 10.2 at? Did I not title it? How sad. It's got to be in here somewhere. I don't know what I did with it. Well, if you go back and look in your notes, it's those places where visually you're getting, maybe I put it in here. No. It's these places that you're getting visually your issues. Okay, so where are these places on the graph is kind of what I'm alluding to. It's the places where you have those kinks. Okay, so it's kind of like it goes down and then just reflects back up. If you remember back in Calc 1, those were places where the function was not differentiable, wherever you have kind of a kink. The main example of that back in Calc 1 was the absolute value function. Okay, so the absolute value function is not differentiable at 0. Okay. In particular, because the left and the right derivatives are different. So coming in from the left, the slope's always -1. From the right, the slope's always +1. And this will be kind of the same deal. Okay. Okay, so and the homework, it's not really a big deal, and it doesn't come up all that much. It's usually you suppose it's going to be smooth, and don't worry too much about it. Okay. So anyways, let's move on then. We need then the derivative in this new kind of setting. Okay, so what is the derivative for us going to be? The parametric form of the derivative. Because we've had all of these kind of translation equations, we kind of expect to have a way of translating back from the derivatives, the parametric to the rectangular derivative. So basically from the book, if you have a smooth curve, so if a smooth curve, big C is given by a set of parametric equations, so given by f of t so x equals f of t, and then y equals g of t. Then the slope at the point x comma y is given by, just as we would think, the derivative of y with respect to x, but what we're going to do is kind of put the derivative of y in the top, so that would be basically the derivative of y with respect to t, and on the bottom we put the derivative of the x with respect to t. And of course that will just be your g prime of t all over x prime of t, which is f prime of t. Okay. And we'll assume that the derivative of the denominator is not equal, can't be equal to 0. Okay, so that'll clear up the cases where we have kind of asymptotes, and also it'll allow us to avoid the smoothness. Okay, the smoothness issue. So, anyways, let's kind of apply this to some problems. So so it's just some example in the book. Maybe I should look on my math lab here in a sec. So find the derivative of y with respect to x, given x is equal to sine squared of theta, and then y is equal to cosine squared theta. Okay, so in rectangular coordinates, you can convert this and figure out the derivative there. If you were to do so, just recall, the Pythagorean identity, cosine squared plus sine squared is 1. So in this case, you could replace cosine squared with y. You could replace sine squared with x. And this thing should be the equation of a line, y equals negative x plus 1. So the derivative, y prime, will just be the slope of that, which is negative 1. Okay, and we should get the same thing doing this derivative in this different manner. So let's take a look, get the derivatives here. So we have x prime. I have to do a power rule, 2 sine theta, and then a chain rule times cosine theta. And then y prime will be 2 cosine theta, and then times the derivative of cosine is negative sine theta. So it's negative 2 cosine theta sine theta. And then for the derivative of y with respect to x, we have the ratio of those two. So negative 2 cosine theta sine theta all over 2 sine theta cosine theta. And of course that just equals negative 1, okay, which is what we got using the rectangular version. Okay. So it's pretty easy. The only thing that's a bit different is the higher derivatives. So you're not just going to be able to take the derivative again and get the higher derivative. So let me give you the formula then for the higher derivatives. And so the second derivative of y with respect to x, the way you think of it is taking the derivative of the first derivative, right? And in order to get a nice formula, and we need to put everything in terms of t. So you can rewrite the derivative of this thing with respect to x as the derivative of that thing with respect to t all over the derivative of x with respect to t. Okay. And you can kind of note how that would work if you just sort of rewrite that prefix as using the chain rule. So this is the same as the derivative with respect to t times the derivative of t all over derivative of x. And then you could rewrite that as a derivative with respect to t divided by the derivative of x over t, and then that would give you kind of that expression. And of course, we're worried about something, right? Some u or something like that. Okay. But the long story short of it is that you can't just find the derivative by taking the derivative again. So anyways, let's zip into WebAssign and maybe do one of these. Here's one. Okay. So this is like problem number 4 in WebAssign. X equals square root of t, y equals 3t minus 7, and we want to evaluate each of these at the point t equals 1. Okay. So first, let's get the derivatives. So get the first derivative. That'll just be the derivative of y is 3 all over the derivative of x. So that would be 1 all over 2 square root t. Rewrite that. That'll be 3 times 2 square root t. In other words, 6 square root t. And then evaluate it at 1. The way they usually write that is to put this big line there and then write t equals 1. Okay. So the answer here will be 6 when you evaluate it. And that represents the slope. The first derivative is the slope. Okay, so as you look over at the answers, the first answer they just want the 6 root t. And then the third answer is the 6, evaluating it at t equals 1. All right, so let's get the second derivative. Y over dx2. And eventually we want to evaluate it at 1. Let's just get the second derivative first. So it's going to be the derivative with respect to t of the first derivative in the numerator. Okay, so we have 6 square root t. And the denominator, though, it's the derivative of x with respect to t. So basically, you're going to be putting this thing in the denominator. Okay, so just for the sake of completeness, let's write it out. So this will be the square root of t. Okay. All right, so the derivative with respect to t of 6 square root t will be 6 all over 2 root t, and then all over 1 all over 2 root t. And just remind yourself, what is the derivative of root t? Root t is the same as t to the 1/2. So if you take its derivative, y prime, you bring down the 1/2, and then you get t to the negative 1/2 when you do your power rule. So that'll be 1 all over 2t to the 1/2, which of course is 1 over 2 root t. In case you were wondering, how do you get those derivatives? What is that? Okay. You could simplify this, of course, and you're just going to get 6. Okay. So that is the second derivative, which you would put in the second box here. But the concavity would also be 6, because what you're doing is evaluating this at 1 again. And there's no t to put in there because it's a constant function. There's no t, so you just get 6 as your output. And that's the concavity. The second derivative is concavity. So you would type in 6, and then it's positive, so it's concave up. Okay. The next kind of problem you see a lot, they want you to find the equation of the tangent line at the point. So let's try that one. Okay, so I have x is t squared minus 4. And then y is t squared minus 2t. Okay, so first I'm going to get the formula for the derivative. I'll just be 2t minus 2 all over 2t. And then there's not much simplifying there. For the points, so they want equation of a tangent line at 0, 0. You need the t value then to get the slope, right? So the t value that's kind of suggested by this point, you could kind of back engineer it by putting 0, 0 into the original equations. Okay. So what do I mean by that? You're taking this 0 and you're plopping it in for x. So you get 0 is t squared minus 4. So t minus 2 times t plus 2. So you get two possible solutions. You need to figure out which one you're using by plugging that other number into the second equation. Okay. So when I plug in 0 for y, I get 0 equals t squared minus 2t. Factor out the t, I get t minus 2. So t will equal 0 and 2. So you look for the one that's common to both, and that'll be 2. So for the first line, the slope, I mean, we have a point, but we just need the slope. The slope will be plug 2 into that derivative. So you get 2 times 2 minus 2 all over 2 times 2. So 4 minus 2 is 2 all over 4, so 1/2. And so you plug everything into the formula y minus y1 equals m times x minus x1. So the point is 0, 0. So there's that. And then I'm plugging 1/2 in for the slope. So you get y equals 1/2 x. And if you look over to the right, that's the first answer. Okay. Let's try another one then. So -3, -1. See if I can move my, it's not allowing me to move my thingamajigs. Go away. Okay, so again, I just let -3 equal t squared minus 4. So t squared will equal 1. So t is plus or minus 1. -1 equals t squared minus 2t. So t squared minus 2t plus 1 is 0. T minus 1, t minus 1 again is 0, so t is equal to 1. So for our slope, you're plugging in 1 for t. So we just take the, all right, so it would be 2 times 1 minus 2 all over 2 times 1 is 2. 2 minus 2, that's just 0. So we get y minus -1 equals 0 times x minus -3. So y plus 1 is 0, so y is -1. Let's make sure that's right. Yep. And then for the last guy, they want the point -3, 3. We already did the x part, so the x part gives us plus or minus 1. Then the y part, 3 is t squared minus 2t. So 0 is t squared minus 2t minus 3. 0 is t minus 3, t plus 1. So it's like t, in this case, is going to have to be the -1. So plug that in for your slope. -2 minus 2 all over -2. So that'll be -4 over -2, which will be positive 2. And so we get y minus 3 is equal to 2 times x plus 3. Y minus 3 is 2x plus 6. And then add the 3 to the other side. So y is 2x plus 9. Let's make sure that's right. Okay, the next one, find all horizontal and vertical tangency lines to the curve. So the thing about working parametric equations, as opposed to just working with the regular derivative, is we're kind of not just interested in horizontal tangents. So horizontal tangents is really important for optimizing functions. So if you remember, the derivative basically would tell us where the maxes and mins were. You just take the derivative, set it equal to 0, find the critical points, do your number line, all that jazz. So in addition to finding kind of the critical numbers, we'll also be interested in finding the places where the vertical lines happen. So section 4, we'll call it horizontal, vertical, horizontal/vertical tangents. So basically, if the derivative of y with respect to t is equal to 0, but the derivative of x with respect to t is not 0, then you have the kind of zero slope case, which gives you a horizontal tangent. So that's like the first case. The second case is then when the numerator is not 0, but the denominator is equal to 0. If they're both 0, then we assume it's not smooth. Okay? So the second case where the numerator is not 0, but then the denominator is. And that'll give us the verticals. Okay, so let's take a look-see at how this goes. Maybe we should look at one of these. Right? Let's do something that's related to what we need to do. Okay, find all points of horizontal and vertical tangency to the curve. Use a graphing calculator probably to... Okay, so we have two functions, x equals cosine theta, and then y equals 2 sine 2 theta. Our parametric equations. This is problem number 7 in the homework. Okay, so you kind of want to find where they're equal to 0, and then you could go back and kind of stamp out where the horizontal and vertical asymptotes are going to be. Okay. So find the derivative first. So x prime is going to be negative sine of theta. And then you can set that equal to 0. On the unit circle, sine is equal to 0 at 0, pi, 2 pi, etc. So we're solving sine theta equals 0, so theta equals 0 plus 2 pi n, and then pi plus 2 pi n, but it really just turns into 0 plus pi n. So theta will be multiples of pi. Okay. This will be where, what did we just find out? This is where the derivative of x with respect to t is equal to 0. It's just reminding myself. So hypothetically, this is where the vertical tangents will be. The only problem is making sure we don't simultaneously have zeros over here with the y derivative. So y derivative is going to be 2 cosine theta of, 2 cosine of 2 theta, sorry, times 2. So that'll be 4 cosine of 2 theta. Set that equal to 0. Divide both sides by 4. And then the places where cosine is equal to 0, where did those happen? That would be at pi over 2 plus 2 pi n. So 2 theta would be pi over 2 plus 2 pi n. And then also at 3 pi over 2 plus 2 pi n. And of course you can combine those into the one version. 2 theta equals pi over 2 plus pi n. And then we need to divide everything by 2. That's from trig, the way we do this. So that means pi over 4 plus pi n over 2. Okay. Do they want to? No. Okay. So this is potentially then where the dy over dt is equal to 0. We want to make sure that's not happening at the on the line y on the y-axis. Okay, so those will be the places where they're simultaneously equal to 0, and then that's kind of an issue for us. Okay, so where are these guys? These are pi over 4 is one of them, and then pi over 4 plus pi over 2. So basically, it's going pi over 4 plus pi over 2 will get us right to here. And then I think it's never going to hit, right? So if you're always adding in pi over 2's, I mean, it's going to kind of avoid the pi over, it'll be at like pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and it'll never be in between, right? So maybe you could see that if you find a common denominator. Because rewriting this, it's going to be 2n plus 1 pi over 4. So it's always an odd multiple of pi divided by 4. So it's never going to be it's never going to be pi over 2 or 3 pi over 2, which wouldn't matter anyways. The only places it matters is if it's at, I was sort of looking at the wrong picture. The only places it'll matter is at 0 and pi. And this definitely never hits 0 or pi. It's only on these 4 sort of dashed lines here. And this one. Okay. That's the only places it'll hit. I'm trying to put it into a different color. Okay, so anyways, let's figure out then where these are. So we know the theta values so the theta where it's vertical are pi times n, and the theta where it's horizontal will be 2n plus 1 pi over 4. Okay. And then we could put those into our original functions and figure out the xy values. So I got to remember my original functions. Let me write them here. X equals cosine theta, and then y equals, I thought it was 2 sine 2 theta, I think. Yeah. Okay, so x is cosine of pi n. And what's happening at those places, right? So n pi is always going to be either 1 or -1. So you have x is either going to be -1 or 1. So we'll just write plus or minus 1. And then the y value is 2 sine of 2 pi n. Okay. When sine is at an even multiple of pi, sine of that value will be 0. Okay, so this will end up just being 0, and so we'll have vertical tangents at -1, 0, and then 1, 0. Okay. So if you look at your vertical tangents, there they are, -1, 0, and 1, 0. So it looks like the horizontal ones are a bit more complicated. So first, x equals cosine of 2n plus 1 pi over 4. And again, on the unit circle, where are those places? So those are going to be here, 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 and here. So there's actually 2 answers for cosine of those angles. Either cosine is positive root 2 over 2 or negative root 2 over 2. So you get positive 2 root 2, positive root 2 over 2. Or x equals negative root 2 over 2. And then you have to think about how is sine kind of associated with those as well. Anyways, sine of, it'll be 2 times that thing, so 2n plus 1 all over 2 times pi. So odd multiples of pi over 2. So those guys will be, like 3 pi over 2, 5 pi over 2, 1 pi over 2. They're always going to be on this y-axis here and then down here. Okay, so that's going to give you positive 1 and negative 1s. Okay, so it'll either be positive 1. But it'll be times 2, right? So you get 2, and then we have -2. And so what you're getting are basically like 4 versions depending on where you are. So if cosine, supposing cosine is right here, you would get the root 2 over 2. And with regards then to, so that would be where n is equal to 0. That would be pi over 4. So downstairs, when n is 0, that's just going to give you pi for sine. So one coordinate will be root 2 over 2, comma, positive 2. Because if you put in 0 for n into the second formula, so all I did was go let n equal 0. In the first formula, I get x equals cosine of 2 times 0 plus 1 all over 4, so you get 1 over 4 pi. 1 over 4 pi is just root 2 over 2. And then for y, you're going to get 2 times the sine of plug in n equals 0, you get pi over 2. So that's just going to be 2. Okay. So that's for that first angle. And then the second angle, I'll put in like green here, this angle, you try n equals 1 for that. So n equals 1 is going to give me x equals cosine of 3 pi over 4, which of course is the negative root 2 over 2, because cosine is negative in the second and third quadrant. Okay, so I get 1 negative root 2 over 2, and then comma y would equal 2 sine of 3 pi over 2, which is going to end up being negative 2. So negative root 2 over 2 comma negative 2, and then let's get this third one. I'll put it in yellow. So for the third one, I'm going to let n equal 2 and etc. Okay, so what's going to happen is basically this one will give you the negative root 2 over 2. But then for the sine, when you put in 2, you'll get 5 pi over 2, which is 1 pi over 2, 2 pi, 3 pi, 4 pi, 5 pi over 2 is positive. Okay? And then for n equals 3, I'll write it in red, you're going to end up with 7 pi over 4, which is this angle here in the fourth quadrant. So it'll be positive root 2 over 2. But then the sign will be negative, because it'll be 7 pi over 2, which is 1, 2, 3, 4, 5, 6, 7 pi over 2 is down here. So it's negative, and this should be a 2, not 1. Okay, so you get all like 4 variations of root 2 over 2, comma 2. And that's what this is. They didn't rationalize the denominator. Okay. And they want some sort of ordering, smallest to largest y. Oh, I see. So from smallest to largest x, and then from smallest to largest y. So first you would get, which one would be the first one? Smallest to largest. So this would be the first one, and then this will be, nope, whoops, this is the first one because it has a negative 2 is smaller than the positive 2. Then this would be the second one, and then this would be the third one, and then this would be the fourth one. Okay. Okay, so the last topic in this section is arc length, and we've seen the arc length formula before. So anyway, section 5, arc length. And we could kind of derive this formula from the arc length formula from before. So from before, we had the integral from a to the b of the square root of 1 plus f prime of x squared dx. Okay, so the trick is to just simply replace this part with its new parametric formula. So dy over dt all over dx over dt. So we have the integral of the square root of 1 plus dy over dt all over dx over dt, and that thing's squared. And then we could factor out dx over dt. So I should write it like that. So put the integral of the square root of basically 1 all over dx all over dt times, this will become dx over dt squared. So this should be squared. plus dy over dt squared dx. And then you could use the properties of radicals to kind of factor out this thing. And that'll become then the integral, and I'll factor it out the back of the square root. So we get dx over dt squared plus dy over dt squared. And then you get 1 all over dx all over dt times dx. And then finally, you can rewrite this part as dt all over dx times dx, and the dx is kind of canceling, you just end up with dt. Okay, and that becomes the new formula for arc length. So let's try one of these examples. We're given x equals 6t squared, y equals 2t cubed, and we want to find the arc length of that curve going from 1 to 4. Okay. And it's pretty much just plug and chug. So x prime is going to be 12t, y prime will be 6t squared, and then you dump it into your integral. So the arc length will be the integral from 1 to 4 of the square root of 12t squared, which will be 144t squared, plus 36t to the 4th dt. Okay. And then that'll be the integral of, let me do a bit of work here, 36t squared times 9 plus t squared dt. And you could factor out the 36t squared, and then it's a u sub. Okay, so we get 6t times the square root of 9 plus t squared dt. And we're letting u be 9 plus t squared. Right. Actually, it's 4. It's not 9. Sorry. 144 divided by 36 is 9. Is 4. Sorry. Did it again. This is 4. 2. This is 4. Okay. Okay. So, anyways, du is 2t dt, and then dt is du over 2t. This will be then the square root of u times du over 2t. Kind of nice to go back and just do an integral after all of this. 6 all over 2 is 3. I'll factor that out. The t's cancel, and you just have u the 1/2 du. So it'll be 3 times, power rule it, 3 to the now 3/2 times 2/3. And we have to evaluate eventually. So this will be 2u, it's back sub, 9 plus t squared to the 3/2, and then we could evaluate from 1 to 4. So this will be 2 times 9 plus 16 to the 3/2 minus 2 times 9 plus 1 to the 3/2. And there's not going to be a nice ending to this story. So just go to your calculator and go to 156.52 is the answer. Okay, we'll make that one the video quiz question. I sort of forgot to put it in there. Video quiz, video quiz, video quiz. Sorry. Hopefully you watched to the end. There's your reward for watching to the end. Okay. I make sure I got the right video. Quiz sections. This should be for homework number. Yeah, this is the last homework. It'll be worth 5 points. So 10.3 is this arc length problem. So x is 6t squared. Y is 2t cubed, and so forth. Okay, thanks for watching, and we'll see you next time.